Hello and welcome back to our statistics series for ENIGMA-U. Last lecture, we talked about how we use probability to get a representative sample from a population. Today, we're going to dive into the first of our inferential statistics, which, if you remember, that's how we go back from a sample, from the conclusions we make about a sample to making conclusions about a population. So we've talked about how to go from population to sample using statistics. Today, we're going to talk about how to go from sample back to population using something called a hypothesis test. Some of the tools that we're going to use today are, we're going to use pretty much all of the symbols we've learned thus far. So if you need a reminder of these, take a picture, write them down, take some notes. We will be using these today. The formulas we're going to be using, we're going to go back to that standard error of the mean formula and the z-score for samples formulas we talked about. And we are also going to go back to that sampling distribution of the mean concept from last lecture. So let's actually do a quick review of the sampling distribution of the mean and of the standard error, just so we have those fresh in our head. So if you will remember, population distributions are composed of individual scores, but psychologists and other scientists often will perform their studies on samples rather from that population. So we need to understand sampling distributions, which are basically made of statistics from every possible sample that is drawn from the same population. The specific sampling distribution that we care about and that we talked about a lot last lecture was a sampling distribution of the mean, which is essentially just taking all of the possible samples from a population, finding the mean of each of those samples, and graphing that distribution. That is the sampling distribution of the means. And then the central limit theorem we talked about is a theorem that describes the shape, the central tendency, and the variability of the sampling distribution of the mean. And it says essentially that as the sample sizes increase, the sampling distribution of the mean becomes closer in shape to the normal distribution, regardless of the shape of the original population. Do that every time. Some more important things about the sampling distribution of the mean is its characteristics. So remember that the mean of the sampling distribution of the mean, or the expected M value, is the same as the mean of the population from which the samples were drawn. So M is equal to the mean of the population. The standard deviation of the sampling distribution of the mean is called the standard error of the mean. And we talked about that in depth last lecture as well. It is found from both the standard deviation of the population and the sample size, which are shown in this formula for the standard error of the mean. And then quick reminder of the properties of the standard error of the mean, or the standard deviation of that mean distribution. It's smaller, the standard error of the mean, this guy, it's going to be smaller than the standard deviation of the population. It is going to increase as the standard deviation of the population increases, and it is going to decrease as the sample size increases. So in summary, the sampling distribution of the mean, number one, is usually assumed to be a normal distribution when the sample size is more than or equal to 30, which it generally is. It also has a mean that is equal to the population mean and has a standard deviation that is the standard error of the mean, or the standard deviation divided by root n. So in order to determine whether the mean of a particular sample, for example, the mean of the sample that you used for your research, to determine whether that sample mean is unusual, relative to the actual population mean, we calculate a z-score for our sample means, and that formula is represented right here. Remember that the differences are, instead, it's exactly like the z-score for individuals formula, but instead of using a raw score, we use the sample mean, because that's our raw score for the sampling distribution of the mean. We use the population mean again, and then we use the standard error of the mean instead of the standard deviation. So remember this formula for later. Okay, let's talk about hypothesis testing. So hypothesis testing is one of the most commonly used inferential statistics procedures. And although the details of what a hypothesis test is change from one situation to another, the general process remains the same. And all hypothesis testing are statistical methods that use sample data to evaluate a hypothesis that you made about the population. So essentially all science that you will ever do in psychology. It's going to combine the concepts of z-scores, probability, and the distribution of sample means, which are all things that we've talked about recently. The underlying logic or the process that we're going to use for every single hypothesis test that we ever run are in the following 5 steps. Number 1, we are going to state a hypothesis about a population, any hypothesis, and we'll get more into all of these steps later. The second step is that we're going to choose and define what method is going to be best to make a decision about that hypothesis. Once we figured that out, then step 3, we will obtain a random sample from our population, and step 4, compare the collected data with our predicted hypothesis. And as we compare that data, we're going to make a decision whether or not our hypothesis was correct. The general goal of hypothesis testing is going to be to rule out any chance due to sampling error as a plausible explanation for the results from a research study. We want to rule out the chance that any differences from our sampling mean to our population mean are because of chance. We want to say they're all because of treatment effect. That's the goal of a hypothesis test. So the hypothesis testing that we're going to start out with today is arguably the simplest version of it. It's called the one sample hypothesis test, and we will use this as the framework from which we build on to learn the other hypothesis testing in the future. So the purpose of the one sample hypothesis test is to determine whether the treatment that you as a researcher have done has an effect on the population mean. So you have a known population before your treatment, you put it through a treatment, and then you see if the population mean changes. Because if the population mean changes enough, then we can assume, or we can say possibly, that there was a treatment effect. This key here is very important. We're going to use one sample mean that we actually do the treatment on to test the hypothesis about the population mean. And if we notice that the individuals in our sample are noticeably different from the individuals in our original population, then we need to make a decision about between 2 explanations for what that difference could be. The first explanation is that the difference is there and it's only because of sampling error. It's a random chance. There was no real effect from the treatment. The sampling mean was different from the population mean just due to sampling error. The second explanation is that the difference is too large to be explained by sampling error, which means that the effect must have been from the treatment. So this hypothesis testing is all about figuring out which of those is the correct explanation. A hypothesis test is a formalized procedure that follows a standardized series of operations, those 5 steps that we talked about in the beginning. And in this way, we as researchers have a standardized method for evaluating the results of our own research studies and reporting them to other people so that we can evaluate their research studies as well, and vice versa. This is going to be the general structure of all of our hypothesis testing. In research, we assume that the parameter mean is known for the population before the treatment. We know that the population mean is about an 80. We then will select a sample from that population that hypothetically has the same mean-ish. And then we're going to administer the treatment to a sample because we cannot plausibly administer treatment to a whole population, right? So we're going to take a smaller sample, administer treatment to them, and then we are going to take the statistics that we get from our treated sample and hypothesize or draw conclusions about what the unknown treated population would look like if we gave all of them the treatment. So the treated sample is going to represent the treated population. And we use the results obtained from them to infer what would happen to a treated population. For that reason, we still state all of our hypotheses about the population, not about our sample. And we'll see that in a second. We'll see that right now. Let's go through the steps of a hypothesis test. There are going to be 4 specific steps that we're going to do for the one sample hypothesis test. The first step is to state our hypothesis. And there are 2 types of hypotheses that we generally state in hypothesis testing. The first and most important of the 2 hypotheses is called the null hypothesis. The null hypothesis is going to state that the treatment had no effect. There was no change, there was no difference, there was no relationship that exists. Nothing happened, hence the name null. In the context of an experiment, the null hypothesis predicts that the independent variable had no effect on the dependent variable. And the alternative hypothesis, on the other hand, states that there is an effect, that there was some change, difference, or relationship that exists because of the treatment that we administered. Note that the alternative hypothesis here states that there was some kind of change, but it doesn't necessarily tell us what direction that change is in, positive or negative. There are going to be some circumstances in which it's appropriate for the alternative hypothesis to differentiate a direction, but not in every situation. So we'll just keep that in mind. This is just a chart that shows us the overlap. We'll add more to this later as we learn more about hypothesis testing, but generally null hypothesis is shown here, no effect exists, alternative hypothesis that an effect does exist. So step 2 is going to be setting our criteria for a decision about our hypothesis. Eventually, you as a researcher are going to use the data from your sample to evaluate the credibility of the null hypothesis, right? You're going to use that data to make a decision. So the data is either going to support the null hypothesis, or it's going to give us enough evidence that we can refute the null hypothesis and reject it. So to formalize our decision process, we use the null hypothesis to predict the type of sample mean that we should obtain if there is no effect from the treatment. We can see that here in the sampling distribution of the mean if the null hypothesis is true. Here are all of the possible outcomes of our sample mean, right? What our sample mean could possibly be. If we get a sample mean that falls close to the null hypothesis, we say that it's within our critical zone. It's a high probability value that the null hypothesis is true. So if our value lands within this region here, we're going to accept the null hypothesis, say the mean is not different enough from the original mean to give us the idea that there was any sort of treatment effect. However, if our value falls in these extreme low probability values, this is where we would say that the mean is different enough from the original mean that it is very, very unlikely that the null hypothesis is true. In other words, the mean has changed enough, it's different enough that there was probably a treatment effect. That's what it means when your result lands in these tails. These are sample means that are very unlikely to be obtained if the null hypothesis is true. So this figure is just showing our sample means divided into those 2 sections. So this is well and good. This is what it should look like. But in order to make an actual decision, we need to determine what these boundary points are. We need a numerical value for these boundary points. And that is where this alpha level comes in. To find the boundaries that separate the high probability values in the middle from the low probability samples on the outside, we need to define exactly what we mean by low probability and high probability. And this is accomplished by selecting a specific probability value, which we call the alpha value, and establishing it as the cutoff for making a decision about the null hypothesis. It's the thing that sets up our critical region in the middle. Excuse me. By convention, Commonly used alpha levels are 0.05 or 5%, 0.01, 1%, or 0.001, which is 0.1%. And we'll get more into this in a second, but the critical region is going to, on the outside, is going to consist of outcomes that are very unlikely to occur if the null hypothesis is true. And we're going to, if, for example, if we selected alpha equals 0.05 as our alpha value, that means that we're going to separate the most unlikely 5% of the sample means, the extreme values, that's what this means, from the most likely 95% of values in the middle. And those extremely unlikely values, those 5% on the outside, make up what we call the critical region. Like it says here, it's defined by sample means that are almost impossible to obtain if the treatment has no effect. And we find the Z value, we call it the Z critical value, that is associated with that critical region using the proportion in the tail column from our unit normal table. I'm not going to show that right now. We will get to that later in some of our later lectures, but you essentially use the unit normal table to just find a numerical value when your alpha is 0.05 or 0.01 or 0.001. And I'll show that right here. So what we're seeing here is this diagram shows how the probabilities of the sampling distribution of the mean would be divided if we establish the alpha as 0.05. What that means is that we would have to, if the alpha is 0.05, that means we're separating the most extreme 5% of values from these high probability values in the middle. Since we have two tails, one on either side of our normal distribution, we need to divide our 5% alpha value into two. So 2.5% of that is going to be in this upper tail, and 2.5% of that is going to be in this lower tail. Using our unit, excuse me, I need to drink water. Okay, using our unit normal table, we can find that at the alpha level 0.05, our Z critical value or our boundary is going to be positive or negative 1.96%. So what that means is if our Z value is either more than positive 1.96, or if it is less than negative 1.96, then we're saying that that Z score is falling in these extreme critical regions, which means that it is very unlikely that the null hypothesis is true, or in other words, we probably have a treatment effect. After we've established that, the step 3 is to collect our data and to compute our sample statistics. Note that we collect our data after the researcher has already stated the hypotheses and made a decision about what alpha level we want. The reason for that is it helps to ensure that researchers make honest and unbiased decisions regarding decision criteria, and we don't make them after we've already seen the results, because that would lead to biased science, right? So after we've already established that decision, we're going to collect our data, we're going to compute our sample statistics, and the sample statistic that we care about is called the test statistic. In this case, it's going to be for a one sample Z test, the test statistic is going to be computed using this Z-score formula that we talked about at the beginning. You take your sample mean, you find the distance from the population mean, and you divide it by the standard error. Notice here that what this is doing is it's forming a ratio that compares whatever our obtained difference is, what the real difference we got between our sample mean and our hypothesized population mean, and comparing it to the amount of difference that we would expect without any treatment effect, which is our standard error. And that helps us figure out how likely this treatment effect or this result is to have been found because of the treatment or independent of the treatment. In the lectures that follow, we're going to introduce several other test statistics that are going to be used in a lot of different research situations. but most of the new test statistics are going to have the same basic formula as the Z statistic. We just use them in slightly different ways and change some of the variables. So this Z statistic is what we're using right now. We'll learn about the T statistic later. Just remember that test statistics have the same basic structure and they serve the same general purpose, which is to just test a hypothesis. So step 4, after we've done all this, is we need to make a decision. If we make our Z statistic, this guy right here, and we find that it is that's in the critical region, it's outside those bounds that we've decided in step 2, then we're going to conclude that the difference is significant and that the treatment has a statistically significant effect, and then we can reject the null hypothesis. But if our test statistic is not in the critical region, if it falls within that middle section of the graph, then we're going to conclude that the evidence from our sample is not sufficient to support a treatment effect. And so we fail to reject the null hypothesis. The mean in that situation, the mean is too similar to the population mean to justify a treatment effect. Okay, here is a brief summary of each of those steps. If we were to determine if the treatment had an effect with an alpha of 0.05 using a Z statistic. Remember, step 1, we make a hypothesis about what the value of the population mean will be after the treatment. The null is that the mean the mean after the treatment is going to be the same as the mean before the treatment. The alternative hypothesis is that the population mean after treatment will be different than the population mean before the treatment. And remember, we're going to always state hypotheses in terms of the population. That's why we're using this value here and not an M. Step 2, you're going to plug your hypothesized value in the formula along with your other values. Well, actually, the real step 2 is you're going to make a decision about where your Z critical values are going to be, but we've already done that up here. We've already established that alpha is 0.05. So then after we do that, we're going to plug the statistics that we got into our test statistic formula. Remember that we're going to use sample statistics to infer population parameters. So that's why we're going to use our sample mean to infer the value of the population mean post-treatment. And then our last step is if we get an extreme Z score that's in that critical region, we're going to reject the null hypothesis. And if we get a Z score that's near 0 or near our mean, then we're going to conclude that the null hypothesis was correct. Okay, there's that summary. Let's do an example really quickly with a realer situation. So let's say that our question was, do children who grow up in homes without access to television have higher IQs than children in the general population? The population statistics are the population mean pre-treatment is 100 and the standard deviation is 15. First step, we're going to state our hypotheses. So our null hypothesis, remember, is that there's no change. So in this context, it would be that the IQs of children without TV do not differ significantly from the IQs of children in the general population. The alternative hypothesis, on the other hand, would be that the IQs of children without TV do differ significantly from the IQs of children in the general population. Note here that the alternative hypothesis just stated that the IQs would be different. It didn't say lower or higher. This is not a directional hypothesis at this point. The next step is we're going to set our criteria for decision before we're doing any of the analysis. And that's what we do here. You would really honestly have to set this before. A lot of times we'll just put it in the description of the statistics, but know that we set this alpha level before we collected any of these statistics. So after we've set this alpha level 0.05 and figured out what our Z critical values would be, remember, for 0.05, our Z critical is 1.96. Let's say we drew a random sample of 25 kids from homes without television, and we measured the IQ, and we got a mean sample, or a sample mean, excuse me, of 103.9. And the question is, can we conclude that children without TV truly have higher IQs? In this situation, we said higher because it was here, but remember the alternative hypothesis just says different, with an alpha of 0.05. So we would find the standard error using our formula here. We would take the sample, the population standard deviation, plug it in, and the sample size of 25, plug it in. Our standard error is 3. We take that and we plug it into our z statistic. So we take our sample mean, our population mean, and our standard error, and we find that our z statistic is 1.3. Remember that we said, now that we have all of our statistics, we're going to compare it to our critical values and we're going to make a decision. So we determined that the critical value for z at an alpha of 0.05 is going to be plus or minus 1.96. So that's our boundaries, remember. The p-value is something that you find with the unit normal table, and we're just really not going to get into that right now. But we found that our z value is 1.30, which is not more than 1.96. It's not outside of that critical value. So it is not different enough from the population mean pre-treatment to justify that there was a real treatment effect. So because it's not more than the z critical value, we fail to reject the null hypothesis. For the IQ of children who grow up in homes without TV, it's not significantly higher than children in the general population with an alpha, because our p-value was more than 0.05. Okay, now we're going to do a practice. I'm going to read through this with you, and then I'm going to have you pause, try to figure it out yourself. And we will come back and check our answers. So Babcock and Marks in 2010 reviewed some survey data from these years and obtained an average population mean of 14 with a standard deviation of 4.8 hours per week spent studying by full-time students. They wanted to determine whether or not this average has changed in the past 10 years. So they selected a sample of 64 of today's college students, and they got a sample mean of 12.5. So we're using an alpha of 0.05, which means that our z critical value is going to be plus or minus 1.96. My question for you is, does this sample indicate significant change in the number of hours spent studying? So remember, go through our steps. Make your hypotheses, write them out. Calculate your test statistic, your standard error, and your z statistic, and then compare it to your z critical value and make a decision. Okay, take a pause, and I'm gonna take a drink of water, and we will come back in one moment. Okay, so let's go through this together. So the hypothesis, excuse me, the hypotheses are as follows. Our null hypothesis is going to be there's no significant change in the number of hours studying between students from 10 years ago and students today. The alternative hypothesis is that there is a significant change in the number of hours studying. We don't say if there's more or less, we just say the hypothesis is that there is a change. Now, since we've already established our alpha values here, we've established our decision criteria, we're going to solve for our standard error, which is going to be 0.6, because we take the population standard deviation and the sample size, and then we plug all of that into our z statistic. The z statistic is going to come out to be negative 2.5, and negative 2.5 is less than our z critical value of negative 1.6. That means if you imagine that graph, it's going to be on the outside of the negative tail, which means that there is enough evidence that the mean of our sample is different enough from the mean of our population. It has changed from the mean pre-treatment. So there's enough evidence to suggest that the null hypothesis is false. And now we can reject the null hypothesis and say that there is a significant change in the number of hours studying with a p of less than 0.05. Okay, and with that, we're going to end our discussion about the one sample hypothesis test, and we'll move into some other hypothesis testing in our next lecture.